Hello and welcome back. In today's video, I'm going through exercise 1.33 from the Art of Electronics. And in this exercise, we need to show at what frequency does an RC low-pass filter attenuate the signal by 6 dBs. 6 dBs is basically when the output voltage is half of the input voltage. And then for the second part of this question, we need to show what the phase shift is at that frequency. So basically the frequency at which we get 6 dBs of attenuation. Before we begin, I just wanted to share that I've started a Discord server for this channel. I'm hoping, we can share our knowledge on Art of Electronics book and any questions. And obviously, you guys have some wonderful feedback on some of the questions that I go through. And it might be a very good place to just share experience and share answers as well. So hopefully you can join this, and I'll try to be as active as possible, but I'll check it at least once a week. So I've got the link in the description as well. Feel free to join or send a request and I'm sure I'll accept it. So now let's go on to part one of the question. So obviously we need to look at low pass filters for this question. So on the left hand side, you can see a low pass filter with your input signal over here. Obviously you've got a series resistor and a parallel capacitor to your load, which would be connected to this end here. So as we have done a number of times in the past, let's first analyze how this circuit behaves. So obviously just looking at it as a potential divider with our, let's say, resistance 1 and quote unquote resistance 2 over here, we would have the resistance of the capacitor divided by the resistance of R1 plus the resistance of the capacitor. So that is basically the total impedance of the circuit, and on top you've basically got the impedance of the capacitor multiplied by your input voltage. So you'll notice that this is the same equation as the potential divider equation. However, the impedance of the capacitor is not as simple. You basically have this variation over here that you have to replace in this case. So adding this into this equation, we get the following. So you can see I've just replaced XC with 1 over j omega c. And then simplifying that a little bit, we get, so bringing this bit down here, we get 1 over j omega c in brackets r plus 1 over j omega c. So you can see from there that this will become j omega c r. And when you multiply this with this part, the top and bottom will basically cancel, and you will end up with just 1. So as you can see over here. Now conventionally we would write the imaginary part second, so I've just rearranged the equation over here. So we've got now V out is equal to V in multiplied by 1 over 1 plus j omega c r. Now just bringing the last equation to this new slide, taking the magnitude of this equation. For those who don't know how to take a magnitude of a complex number, it is basically equal to the square root of your real part plus the square root of your imaginary part. So doing that for our equation over here, we end up with this. So on top, you just get the square root of 1 squared, which basically ends up as 1. And then on the bottom, you can see I've got 1 squared, which is basically 1 plus omega squared, c squared, and r squared. Obviously, I've covered this in more detail in my previous videos, so feel free to check them out. There are quite a few questions in the Art of Electronics that focus around low-pass filters, so we've been through this multiple times already. Now, just bringing the last equation to the new sheet over here. So this is basically the response of an RC filter in terms of its magnitude. And we know that from the question that we are attenuating the signal by 50%. So our V out divided by V in is equal to 0.5. So we can change this equation by bringing this V in onto the other side and making that thing equal to 0.5. So now the equation is 0.5 equals 1 over the square root of 1 plus omega squared c squared r squared. Now doing a square on both sides, you basically end up with 0.5 squared, which is equal to 0.25. And then you can do the square on top and the bottom, which means that you get rid of the square root on the bottom, and on the top you basically end up with 1. Now trying to simplify this equation over here, what I've done is taken this part over here to the other side. So basically multiplying both sides by this denominator over here. So you get 0.25, and in brackets you would get 1 plus omega squared c squared r squared. But I've just expanded the brackets out here as well. So that is 1 times 0.25. And this section over here is omega squared c squared r squared multiplied by 0.25. And then on the right hand side, we're left with the one that's over here. Now, simplifying this equation a little bit further, we basically end up with 0.25 omega squared c squared r squared is equal to 0.75. So all we're doing is moving this to the other side. Now, dividing both sides by 0.25, so that is basically 0.75 divided by 0.25, we end up with 3 on now the left hand side. I've just changed it around. And on the right hand side, or the left hand side over here, we basically get rid of the 0.25. So we end up with 3 equals omega squared c squared r squared. Obviously, for this question, we're trying to find out the frequency at which we get 50% attenuation. So we basically need to bring out the frequency component by itself. So rearranging the equation to get the omega by itself, we end up with this equation over here. Omega is equal to 2 pi f. So we can rewrite the equation as 2 pi f equals square root of 3 divided by c squared r squared. And then finally, we simplify the square root on this. So we get rid of the 2 squares on the bottom, and we end up with just the square root of 3 on top. And taking the 2 pi on the other side, we end up with the frequency equal to square root of 3 divided by 2 pi rc. So this is the solution for the first part of the question. For part 2, there are 2 methods that we can use to calculate the phase response, or the phase shift at the frequency where we get 50% attenuation. So the most important thing for this part over here is doing the phase, is basically calculating the phase of a complex number. So our complex number example I showed you before was this. When doing the magnitude, you obviously do the square root of a squared plus b squared. But for the phase, you need to do, or arctan, b divided by a. So your imaginary part divided by the real part. The frequency response of our filter was this. So the angle on top is basically 0 divided by 1, as we don't really have an imaginary part on the top part here. So it's 0 divided by 1. So arctan of 0 divided by 1, so 0, is equal to 0. And then doing the angle of the bottom section, we basically end up with the real part as 1 and the imaginary part as omega cr. So we got omega rc over here divided by 1, so obviously we've got omega rc. So the total phase shift for this frequency response over here is equal to 0 minus the arctan of 2 pi f rc. All I've done here is replace omega with 2 pi f, and you would get the answer in radians. So if you wanted the answer in degrees, you need to multiply it by this number over here. From phase 1, we calculated the frequency at the 6 dB point is equal to the square root of 3 divided by 2 pi rc. So we can basically replace this f with this equation over here. And we end up with this. So the phase shift is equal to 0 minus arctan of 2 pi rc multiplied by the square root of 3 divided by 2 pi rc. So this part is the f on this equation over here, and this is the rest of it. And you can see I've replaced the f with this. Now these two would cancel each other out. So what you end up with is your phase shift is equal to minus arctan of square root of 3, which is approximately equal to 60 degrees. There is a different method to do part 2, and I'm just going to show you that now. For that method, we're basically going to use something that the book has given us a few chapters before the question. So what this is basically telling us is that we can calculate the phase shift using this equation over here, and all you need to do is do the frequency divided by the cutoff frequency of a low pass filter. So we calculated the frequency at the 6 dB point, which is what this frequency refers to in this question. The cutoff frequency, or the 3 dB frequency for a low-pass filter, is equal to 1 over 2 pi RC. Obviously, we've covered this many times before. So if we try to combine these two together, or look at it as one thing, so the 6 dB point is basically equal to the square root of 3 multiplied by the 3 dB point. So we can rewrite this equation as the square root of 3 multiplied by this equation over here. Now, if we put both of these into this equation so that our F is the 6 dB point and our FC is the 3 dB point, we can basically rewrite the equation that's given here as this equation here. So you notice on the top, we've got this equation, and on the bottom, we have this equation. So the phase shift is equal to the arctan of the 6 dB point divided by the 3 dB point. Now, you will notice that you can basically cancel this out with this, and you end up with square root of 3 divided by 1. So anything divided by 1 is the answer itself. So then your phase shift is equal to minus arctan of the square root of 3. So you can see we arrived at the same answer, but this was a lot faster to get to. And obviously the phase shift at the 6 dB point is equal to approximately 60 degrees. So thank you for watching. If you have any questions, please let me know in the comment section below. And if you want to collaborate on these questions, or if you want to join a community where you can discuss ideas for art of electronics or the other things that we cover on this channel, please join the Discord server.